we're very much interested in organic chemistry in the broad sense, understanding how bonds are broken and formed. And we go from very small molecules in solution to larger systems such as enzymes. And in those cases, we often start trying to understand how the reactions happen, what is driving the intrinsic reactivity of those systems, and how solvent, confinement, or even an enzyme affect the reaction that we're exploring, how we can enhance selectivity and reactivity. And to do that, we use a range of different tools, and we're very pragmatic in that sense. Anything that we need to answer the scientific question is what we will learn and what we will use. And that involves electronic structure methods, molecular dynamics, as most of you know, and more recently, machine learning in different flavors. But we also try to develop different computational tools, and that is mostly to bridge the gap between our experimental colleagues and us as computational chemists. And some of the tools that we have developed is related to reaction pathway search, supramolecular cages. So you can go here online, for example, are using 1D representations, build your own supramolecular cages. This type of tools sometimes are not really set up for quantitative analysis, but help us hugely, our synthetic colleagues, to explore some models and to have a good feeling of what may work and what cannot. And more recently, we have been looking at machine learning. I will mention later today machine learning potentials, but we're also very much interested in retrosynthesis prediction and machine learning in a more traditional way, like using a lot of data there. But today we'll focus more on the more physical approach of machine learning. So as you can see, we cover a range of different systems, and our main interest in all cases is understanding the chemistry that is taking place there. And when we're in between, we are sometimes labeled as organic chemists, sometimes computational chemists. We are fully computational, so we don't do any synthesis. But with that feeling, I think that the words from Charles Colson are very much interesting. Sorry, can I move this?
If I could see my mouse. No, I'm sorry. I think it will take too long because I cannot see the mouse. No.
You can
You need the mouse.
Okay.
On Zoom, everyone can see it.
Yeah. Okay, so you have to believe me that this person is Charles Colson. He was a professor in Oxford, and he was chairing this conference in 1959. That was 30 years after quantum mechanics was developed. And he said that this is the first time kind of the conference that he see this split. And he said, from now on, there will be a separation in the community. Those that will be very much interested in solving the Schrödinger equation, the so-called ab initionists, that were coming from the early 30s, but moving into more applications that led into the posteriores, those interested in obtaining trends, understanding the chemistry behind those systems. And he mentioned that it was very important to keep both communities communicating to each other, because what it was important and what was the key message of this slide, that he said, give me insights, not numbers. Okay, so we want to have insights from those calculations, not only numbers, not only focusing on this. But actually, as computational chemistry now is moving and evolving over time, we can ask actually ourselves to have insights and numbers. So that is what we're aiming for. And from the 1930s, moving into the 90s, for example, we saw a large development in computational methods, aiming at that point to say, actually, we can get insights, but we can also obtain numbers. We can aim higher because we are a much more mature community. But still, if you think about the 19th, that is what was available. Maybe you could do most of the time Hartree-Fock, and your benchmark was an MP2 calculation with a very small basis set. But later, well, DFT was developed in the 70s, but later in the 1990s and 2000 really became a huge development of making easily available different density functional theory approaches. You have these different flavors of them. And you can see that today when we go into running calculations, we don't use Hartree-Fock anymore. We go to DFT, we can do DLP couple cluster and so on, and even full CI for some small system. So we have a wide range of different options depending on the accuracy that we're aiming for and the system that we cover. But still, there are many challenges. And that is because we are aiming to explore complex and more complex systems. And one of them is accuracy. So if you think about enantioselectivity, for example, synthetic chemists really care about enantioselectivity, having an E value of above 90, for example. But if you think about an EE of 0, 50, or 90, you have to consider that this is an exponential relationship between the rates of the reactions and the activation energy, which means that actually an error of 1 kilocal per mole can lead you from 0 to 93 kilocal per moles. Even if you go from one EE, having one enantiomer being the preferred, or the other one, you are moving between this small energy range, which means that we really need accurate methodologies. And often we call the chemical accuracy threshold this 1 kilocal per mole, because we are very much interested in making differences in that area. And in many cases, we are not there. We can understand some cases, but it's still very difficult to predict enantioselectivity. So one of the key challenges actually is developing those methodologies. And that is where the abolitionists are still highly relevant today. But we also have other challenges, and those are related to automating the processes that we do. So we don't run manually 100 transition state calculations. We do that in a much more meaningful and smart way, so we can focus on the chemistry behind. But inclusion of solvent, for example, treatment of entropy, those dealing with enzymes or with the small molecules know how difficult, or even experimentally, you know how difficult it is to deal with entropy. So there are still many challenges, and my group is particularly interested in understanding how we can automate different processes to make calculations easier to run for us and for our synthetic colleagues, and also to understand how we can introduce solvent and entropy effects in a more meaningful way. So for us, our approach is that we think that interpretability remains something very important. Developing the 60s, physical organic chemistry was key to develop organic chemistry. We all learned that in undergrad. And for us, if we can have this backup envelope models, remains hugely important. But we also want to go for accuracy. We want to learn from our colleagues, the abolitionists, introducing those methodologies in an easier manner, and also learning new methodologies. And that has meant for us learning new methodologies coming from machine learning to solve the questions that we want to approach, in particular, how we can automate and how we can introduce physically meaningful models to make more realistic predictions. And today we'll give you an example of each of those areas, very briefly going into the more physical organic chemistry projects that we work on, and later focusing much more in machine learning potentials and automation. So thinking about interpretability, this is one of the projects that I started when I moved to Oxford, that I was in collaboration with Professor Ed Anderson, he's a synthetic chemist, and they were very much interested in these very small, weird strain molecules, so-called. And they are very important because if you think about drug molecules, many people is aiming to escape flatland, which means that anything that has an aromatic compounds, people want to replace them, because that means that if you replace this molecule for this one, you keep almost the same geometry of your drug, but you can improve hugely solubility, permeability, while keeping the activity. So it's very promising, but synthesizing those molecules remain challenging. So many people is aiming to exploit the strain that hold these molecules to activate reactivity. And you have already in the market some drugs that have those scaffolds and that have been demonstrated to be improving all these properties. But it's difficult to synthesize them in large scale. So our first question was to understand why this molecule is stable. That has been discussed over the few years. Why a strain molecule is stable and how we can balance reactivity in that case. And this is a very interesting molecule because actually was predicted in the 80s by Weber, was predicted and synthesized by him. At that point, no one believed that this molecule could be stable. And we started actually to compare that to other strain molecules. So you have cyclopropane, cyclobutane, and we were asking ourselves, all these synthetic papers say a strain release is driving reactivity. And is that really the case? Is the strain release the driving force of those reactions? And if you see in this case, the strain release from those molecules is almost the same. But you see from undergrad studies that this one will be much more reactive. So there has to be something else apart from a strain release that is driving reactivity. A strain release in this case actually is not too different but still this is order of magnitude more reactive than any of those molecules. So we started to study that using basic DFT methodology, but we started to realize actually that we needed to go higher. We tested a few CAS 4.4 and so on. But here is just an example that show you if you localize the orbitals and you allow the localization, you can see in this case that this bond that we tend to draw here actually disappear because this cage molecule, what is allowing is to delocalize the electron. It's an sp3 molecule, but you can see it's delocalization. So all this blue area is showing that the electrons are being delocalized around the cage. And that is very important for stability, because if you remove this delocalization and you localize your orbitals, you have an increase in energy of almost 20 kilocalories per mole. So key of the for the stability of this molecule is to have this delocalization. And this delocalization also explains why this molecule is so promiscuous, can react with nucleophiles. And you see here that these molecules can retain the electrons coming from this nucleophile and allow the delocalization of the system without being broken. Can react also with electrophiles, and in this case is giving away the electrons coming from that are being delocalized, and that means that the cage has to open. It's not stable anymore. And that also explains why we don't have dimerization that is very common in other strain molecules. So if you think about 2,1,1 propellant, so adding just one more carbon, you see a different behavior. And you have that polymerization is more favorable than other type of reaction. So using the small models, we're able to explain the different reactivities that we were looking at and actually exploring different synthetic pathways, how we'll react with nucleophile and with different electrophiles. Okay, so can we go to a bigger, larger model that can predict different reactivity for other strain-like molecules? So with this comparison, we started to look at, going back to the question here, that a strain was not only the driving force for enhancing the reactivity of these molecules, delocalization was the other factor, because delocalization, what allows you to do is to have an early transition state. And you see that the interplay between the two of them is what is allowing the reactivity of this molecule to be so high, but still the system is so stable. And that can be shown here. If you do a normal Marcus equation, for example, just based on driving force, you see that there is no correlation between all these strain molecules. So we are comparing here with different nucleophiles and radicals addition. But actually, if we introduce delocalization as a parameter in this equation, we see a very nice correlation. And delocalization initially was accounted for through NBO analysis, but more recently, we developed this very simple rule of thumb that is for every 3-member ring that you add to the bond, you have a 10 kilocalories per mole stabilization energy. And just with these parameters, so you have the strain energy of these molecules, and you count the number of 3-member rings attached to the bond that is being broken, you can see that delocalization can be accounted for in a very simple manner, and you have a very nice correlation. So in this way, we are able to make predictions and to compare the 3,1,1 to the 1,1,1 propellant and to analyze the reactivity on this system. So this rule of thumb tells us that the reactivity of the system will not be too different in this case for the where we have the radical addition, and that was the case. Energies differ slightly less here when we go for the full calculation, but with this rule of thumb, we're able to identify which nucleophile, which radical will be the more favorable to react. And indeed, we were able to more recently synthesize those molecules and demonstrate that this 3,1,1 propellant can also act as a drug-like scaffold in those systems, replacing the original aromatic compound. So there has been a very nice interaction between experiments and computation. And still is one of the key aspects of our work. So we were able to show that in this case, delocalization was a key factor that not only works alongside a strain release, but actually is driving reactivity in many cases. We develop a rule of thumb in these cases for cyclic compounds, both just carbon-containing compounds, but also heterocyclic compounds that are so-called strain release systems. And hopefully we are contributing that through interaction with our experimental colleagues to synthesizing new scaffolds that can benefit the development of drug-like molecules. So that has been a very interesting pathway. But we're also, as I said before, apart from collaborating with other experimental colleagues, we are very much interested in developing methodologies and using what is out there to solve our own questions. And that has been the reason that we have been exploring reaction pathway search. So many of you, as undergrad maybe, were interested in looking at a reaction pathway. And if you use any software package out there, you will draw the reactant, the product, and maybe guess with chemical intuition the transition state. And then you have a reaction pathway. That is great because you have the knowledge, but it's time consuming. You have to draw in 3D and that takes time. Some people has been developed and thinking, okay, can we use a computer to really explore all the energy surface, all the different pathways that we can explore? And indeed, since 2000, many people have been working on that. And it's amazing because you don't need any chemistry knowledge, but that means that you have to explore all the bonds that your molecule have, which is expensive if your molecules start to be more than 10 heavy atoms, for example. There is another approach that is between those. So let's automate something, but tell the computer all the pathways that we think are relevant and provide reactants and products, and then identify the transition state. And when we started working on that, there were a few papers. Sadly, many of them were previous to GitHub, so you don't have access to the source codes very easily. And in other cases, they were under a paywall, which we couldn't afford. So we were interested in developing a methodology that will go beyond this 3D model, but we can start from a 1D representation. And indeed, we wanted to make use of all these amazing tools that are now available for us, based on the SMILE representations, using graph representations as well, and RDKit, among other different tools. So combining them in one place. And this is how AutoDE came to life. So this was developed by a PhD student, Tom Young, that graduated last year, and another colleagues in Oxford. So our goal was to use that for organic and inorganic reactions, and we could combine that with different packages. So if you use Gaussian, Orca, QChem, you can use this code just to interface all of them. That was free, and then we can automate sampling. So the tools that were under a paywall, they didn't allow you for sampling. You had to provide a 3D confirmation, and we know now that transition state sampling and reactant sampling is very important. So with that, we started to develop that. And the philosophy behind AutoDE is the following. You start with a 2D representation or a 1D representation, and from that, you generate your graph. With a graph representation, you can count the number of bonds that are formed and broken. And you do that by comparing just the reactant and the product. So in this case, you see that one carbon-carbon bond is formed, one carbon-oxygen is broken. No carbon-hydrogen is broken, so which means that we don't have to spend time looking at those potential pathways. We just focus on all the combinations that will have this forming and a breaking pattern. And indeed, we have many different options. Here I'm just 5, but we have a few more that will have one carbon-carbon bond formed, the other one is broken, but we see that only one is isomorphic to the product. And that will be our starting transition state. And from that, we run the calculations. And this is how it looks like in a Python script. So you have the reactants, you have the products, you provide them in a 1D representation. You indicate the solvent that you want to use, and maybe if you want to calculate a complex or not. Because that means, for example, if you have a Diels-Alder reaction, you don't have a complex, the complex will be higher in energy. But in this case, for an SN2 reaction, in the potential energy surface, you have a minima here. So we also compute that. And Joseph, the student working on that, did explore this reaction, and so a shorter time with AutoDE, but it's still long. But most of the time in this case was waiting in this like a small CPU cluster for the calculation to run. So we run all these steps and you just wait for the calculation to finish, which is a huge time saving, especially when you look at bigger molecules. So we have used AutoDE, for example, to look at this reaction pathway. And the only difference here is that in the last step, you have a Diels-Alder reaction. And depending of the orientation that has can lead to 2 different natural products. Drawing that by hand is a bit more problematic, but with a 1D representation, you can have that and indeed identify without drawing that yourself that the lowest energy pathway is this one because it has an intermolecular hydrogen bond interaction between the carbonyl and the NH group here. We also have been using that for a organometallic system, in this case, aluminum complexes, and again, saving us a lot of time with the conformational sampling, at least in that system. We can look at multi-step reactions, and in that case, we have to provide some intermediates. So there is still the limitation that we have to use our chemical intuition to suggest some potential pathways. And we're comparing this to the work that Morokuma and Ken Hauck did. They very detailedly studied this reaction. They mentioned that there were many different pathways, which is actually most of the time that was taken. They said that they spent a year on that. And we really benefited from that. But you can see that in a day, we can reproduce calculations from that paper. And indeed, using even different software, we're using Orca, they were using Gaussian, we compare both. We can reproduce that and have a small differences here and here because we identify a slightly lower energy transition state and intermediate. But in that sense, you can see that you can save a lot of time rather than manually going through the whole system again. And we have used much more recently that to study reactions in supramolecular cages, where the aim is you study the uncatalyzed reaction, and then you study the reaction inside the cage. And you can use a kind of a docking approach where you check the stability of the reactant, but also of the transition state, because these are kind of biomimetic system. So the idea is that the cage will bind more strongly the transition state than the reactant, okay? But using those systems, we started to see some of the limitations as well. Okay? Because in those cases, you can imagine that flexibility, dynamic of the system, solvent effects, counter ions start to be very important. And that just become a limitation for DFT. So in this case, just to close this one, we can see that chemical knowledge remains for us very important. We want to automate system, but we want to combine this chemistry knowledge with automation so we can reduce the human effort and really focus on the chemistry that we want to explore. But still there are many challenges, and Shubik and others in our group are exploring how we can improve optimizers, how we can make life easier for us, especially when we study transition metal complexes, which surfaces are very complex. Okay, so we haven't solved all the things. We're very far from that, but I think that this is a good starting point. DFT calculation remains a challenge there, so it still is the bottleneck. And that has been one of the motivations to move into the next topic that I would like to mention, our more recent work in machine learning potentials, where we think that we can improve efficiency and go into more realistic models, okay? So for those of you less familiar with machine learning potentials, just let's think about a normal force field. So most of us have been running molecular dynamic simulation. And in that case, you use a classical force field. Maybe you're using AMBER or PLSA or so on. And you see that, for example, for a bond, you can parameterize that in a very simple way, actually, because you don't need many parameters. If you want to parameterize a bond, you often don't use a Lennard-Jones potential, you will go for a harmonic potential. And in that case, you need only two parameters, the equilibrium distance and the force constant, okay? You may have that from a frequency calculation and so on. So you have one point in your energy surface that you know, and then the rest is just parameterized. So very efficient, very transferable to different systems. You may need to modify a bit the force constant, but that is all. But of course, you cannot break any bond. It's fixed. In machine learning potentials, the goal is kind of similar. You have some information of the energy surface, but you may need a bit more information, not only the minima, but a few points around that. So if you have that information, you can fit a function, okay? So you can do a fitting and may work very well around your minimum, but it doesn't work, doesn't interpolate well, but doesn't extrapolate very well. The good thing is that you can use active learning and start adding more and more information that is relevant for your system. So you can go and use a machine learning potential to add more points, run active learning, and then have a better fit. And in that case, the philosophy of a machine learning potential is that you have a reaction, a coordinate, a 3D coordinate, and you can obtain energies and forces. So you put your coordinates in this black box, and you get energies and forces. And from that, you can run dynamics, you can get derivatives, and you can do many, many different things. So in contrast to a normal machine learning model, you don't get a observable directly. You get energies and forces that you use there later to propagate dynamics and to make other predictions. And for that, what we need is a representation. When we run QM calculations, that representation is often a basis set. But in this case, we have to find something else. So we have different flavors of representations. And our aim is always to have invariants. So they can be invariant to rotation, translation, and permutation. And then we have a regression task. What is our ML architecture that will make the connection between representation and energies and forces? So for that, we have different flavors. You may be familiar with the ANI potential that is based in neural network, where you have your input system and the output, and then you train all these weights. We have been using, are much more familiar with kernel-based and linear-based models where you look at similarity. So in the case of the kernel-based, you have a system that is known in your training set, and you calculate the similarity between them, and from that you can estimate the energy, okay? And linear-based models are actually very similar to force field, but just going into higher orders. So actually, we have been using these two different approaches. Transferability is much lower than ANI. It's not general. You have to train for your own system, but the training is way faster. And that is what we wanted to achieve, especially because we wanted to go to organic reactions. So you want to compute a reactive potential. You need information about your minima, but also of the system going away from there. And when we started to work on this in 2019, Marcus Newley in Basel was doing work on that, and was very inspiring to see his first model for an SN2 reaction. It's still very simple, but showing that that was possible. The number of configurations needed still was huge, 300,000, 500,000, and so on. But later, when people started to work in 2021 with active learning, and that is Rafael Gomez Bombarelli, for example, introduced that, you can see that he was able to go an order of magnitude lower in the data set that you need. More recently, Parinello has been also doing reactions in solution, going again an order of magnitude less. But what is important to mention is that all these works, even those ones with fewer configurations, those are coming from ab initio MD in periodic systems. So that means that you're limited to your specific DFT functionals that work for periodic systems, and that you have to run ab initio MD. That is indeed very expensive. More recently, there are some number of configurations that I couldn't quantify because they are just the starting of number of propagations that they do, and from that you get configurations. So you have several thousand more of configurations going on there. What we wanted to have is something that will have 1,000 configurations that you can train. It's system specific, as all of them, but where you don't have to do ab initio MD. Just use DFT calculations. And that is the spirit of what we have been doing so far. So what we have done is combine AutoDE. In this case, we explore the reaction. Often we train from the transition state, and we do random displacement from the transition state. Let's say 10 times. We have 10 configurations, and we start to run dynamics. And we do an active learning loop as many times as we need to have a stable potential. We have introduced now condensed phase calculations, and we can also introduce that information in our active learning loop. When we do the active learning, a key step is to select the configuration. Will we keep this configuration or not? And that has been a game changer and work that has been doing Hanwen in our group, because often what people have been using is energy. So you compare the energy of your configuration. Is that similar to the one that I have? If it's too similar, I don't want to keep that because I already have that in my training system. If it's too different, I also remove that because I don't want to explore that area of the chemical space. But that means that every time you have to run a QM calculation to compute the energy, okay? And that is very expensive. But we did approach, still we started to run that, and we were able to run an SN2 reaction. This was the first example that we showed in 2021. You do an SN2 reaction using the GAP framework, and we train initially. Our first training is a PBE, a GDA functional. We know that it's not good for activation energies, but give us stable configurations. So this is the activation energy that we get with PBE. But later we can do uplifting. So From that, we move a few configurations at a higher level. And now our potential is as accurate as the LPNO coupled cluster model that we were testing. Okay, so now we have a potential that actually can be reached the chemical accuracy with those methodologies. And that is something that you cannot do with ab initio MD. Okay. We were also exploring how we can quantify accuracy, because in many cases, people use correlation. So you calculate the R² between the predicted and computed energies and forces. But what we saw is that sometimes you have high accuracy, then you propagate dynamics and the system explodes. So we started to use this tau value. That was the time that we spend until we accumulate a given error. And that was very important because sometimes you have, this is accepted error, for example, 1 kilocalorie per mole around. And it doesn't matter if you have only few points, but if they are very high in energy, we sum up them and we compute how far we have to go, for how many femtoseconds or picoseconds we have to go until we accumulate that error. Our potentials are often much more stable than that, but give us a feeling of comparing different methodologies, different force fields. Are we improving stability or not? So right now we're using different parameters, not only R² and the error that we obtain from energies and forces, but also how long it takes for the system to become less stable. And we have used now more recently this gap potential for running reactions in solution. So this was the example initial that we have, and also metal complexes as the metallocages that we are very much interested on. In this case, we have a palladium model bound to pyridine complexes here. And we can use symmetry in this case. So we train a model that has pyridine, 1 ligand, and we can translate that into a system that has twice the number of atoms. But more recently, there have been more methodologies coming in. You have seen equivariant models that are very, very useful and very powerful. And we started to move away from the gap model, this kernel-based approach, because it was more difficult to train when we have highly exothermic reactions. Okay. So right now we have developed a methodology that we can just compare the different approaches. In this case, we're comparing GAP, ACE, and NIQUIP. NIQUIP is an equivariant neural network model. And you can see that in all cases, they give you relatively good results. But you see that in some cases, some of them are more accurate. They need less configurations. And this is something that we have seen. In general, ACE and NIQUIP require less configurations and are slightly more accurate. Instead of time, NIQUIP maybe was slower, but it's because our system was small. NIQUIP can scale much more with bigger system. And we have seen actually with ACE, for example, this is an energy surface. We are in the red is ACE, the gray is the true energy surface. And you can see that they overlap completely, which means that we can interpolate and extrapolate. Only on this side start to be slightly different. Okay, so we can see here that is being able to interpolate and extrapolate very well. And we can do, in this case, reactions that we cannot do with DFT. So this is a trifurcating surface, which means that after you pass the transition state, dynamic effects can lead the selectivity of the reaction. So there is one transition state that leads to 3 different products. DFT, it will be a deterministic approach, will give you only one, but with this, you can propagate dynamics downhill and explore how many times you go to each of the systems. And a key example here is to show that we need many configurations, many trajectories, at least 100 to obtain convergence. So in this case, we can go to the reactant back or to the main product and even to the secondary product that we can see for this reaction. But an important message here was that it doesn't matter which methodology we use, which descriptor we use, the most important thing is which DFT methodology we're using for training, because our potential will be as accurate as our DFT methodology. And you can see here that the main differences between the product distribution is the DFT functional that we're using for training. We don't see many difference when we use ACE or GAP or other model, or different descriptors, different hyperparameters. The main difference comes from the DFT model. PBE, as expected, very good for materials, not very good for reactions. And you can see that again, is given the main product to be the blue one, which actually is not the one that is observed. The one that is observed experimentally as the main product is the one here in red or pink each. So again, the results are highly dependent of the reference method, and that is something that we cannot escape. Benchmarking remains key. For this system, we have also introduced nuclear quantum effects, not very important for this reaction because you have just a carbon-carbon bond being formed, but we are using that to explore hydride transfer and some other reactions that can be affected by those effects. And something that has been much more transformative for us and work led by Hanwen and Veronica in our group is to explore different selectors. I mentioned before that the energy selector is expensive because we need to run QM calculations every time. But if you go to similarity descriptors or distance descriptors that are just based in the configuration, so you just see how similar or different they are, you can save a lot of computer time. And we have compared the three different selectors to use in our active learning approach. So this is for water. We did an active learning loop, and we get many configurations until we have something stable. When we use energy selector, we need many more configurations to have a stable potential. Okay, here I'm mapping all the configurations that we have in total. This is the low energy region, so where you have a very nice water complex. And here you have a high energy water interactions going on there. The similarity and distance models, fine, it require very few configurations, but actually sample the whole space. So you have some example of this high energy, a few from the low energy, and a few in the middle. And you see that indeed, when we compare them, the energy distribution between them is much more easily explored by the descriptors that are based in similarity and distance compared to the energy one. The energy selectors serve to be around the minima very, very often. So that means that you are keeping configuration that is slightly different to the one that you have, but not hugely different, okay? So we can use much less configurations if we use this similarity or distance selectors, which are the ones that we're using now, and what has allowed us to go into modeling reactions in solution. This is the first reaction that we have shown, recently reported, we reported that in ChemArchive, actually it's 2023, so just a month ago. And this is a Diels-Alder reaction in methanol and in water. This is just the water one. And what has been key is using the selector, but also how we use the configuration. In total, we have around 600 configurations. And the reason for having so few is that we first provide some based on the chemistry, just intrinsic reactivity, some that describe the important hydrogen bond interactions, and some other that describe the solvent-solvent interactions. So rather than training a full box that have only one solid and a lot of water, where we spend a lot of time trying to learn the chemistry, not very well, in this case, we provide different training configurations. And that is very important because we make sure that we know solid-solid interaction, solid-solvent, and solvent-solvent interactions. And in that way, we can propagate dynamics from the transition state, as you see here, and you can compare the energies and forces for this system. What has been interesting too, if you compare to experiment, you can do free energy calculations. So we can combine now that to umbrella sampling, and we use our potential to run downhill dynamics, but also umbrella sampling calculations where you can identify
some problems with the electricity at heats today, so that might be that. I think everything's back into operation. Recording is in progress. Yeah, sorry for that.
Okay, no, no worries. So in that case, we can see that we have the implicit model.
I wonder if now I can get it.
Yeah, perfect. Yeah, we have a closer agreement to the experimental results here, but also we can see the synchronicity of the process as we go from gas phase to implicit to explicit solvation. So the timing of this asynchronicity between the first bond that is broken, the form, and the second one. And in this case, the solvent effect that we saw between methanol and water can be explained because the hydrophobic effect that you see in the system, you really form a cage, the volume of the cage that you form, you can monitor that and see how it's changing during the reaction. And as I mentioned before, we can use also the potential energy surface and propagate dynamics. And again, we see the same. So from two different approaches, we can see that this intermediate is still existing there and doesn't show up if you just run a DFT calculation. So you can see the time life of this intermediate that quickly decay into the product. So we have been combining these things because we're, as I mentioned before, very much users of the different approaches that have been developed. So we have combined everything here in what we call MLP train, where what we have is we combine that with AutoDE. As I mentioned before, AutoDE you can run from Orca, Gaussian, XTB, QChem, and other things, but this is the ones that we use most of the time. With MLPs, we have included ACE, GAP, NUKIP, and more recently MACE. Very much interested in introducing other. And here in NLP train, we have the different descriptors that I was mentioning before. And more recently, that has been work from Hanwen and Veronica, interfacing that to Plume so we can do active learning using those methodologies of enhanced sampling. So we can use the potential later, but we can also introduce that during the training. So this is just for water, where you say, I want to compute water. This is my starting geometry. This is the ground truth method that I want to use, and this is the dynamic that I want to run during the active learning process. Okay. So with that, I would just like to finish the presentation on this area, and we have been very much interested in exploring MLPs that are maybe not transferable, but easy to obtain. And the locality assumption is important because that allows us to use cluster models rather than the periodic system that you need for ab initio MD. Reference methods remain very important, so we still spend time benchmarking methodologies. That is something that we cannot escape. But indeed, we think that this is the solution to go into more complex model when sometimes QMMM is still not yet there, or where force field are just not well suited. In particular for solvent effects where are involved in the chemical reaction. With that, I would just like to close and summarize the work that we do in our group. We are very much trying to combine as much as we can the interpretability aspect and how we can introduce these different methodologies that are coming in to have more realistic modeling that is accurate, but also allow us to understand new chemistry. And with that, I would just like to thank everyone in the group that has been working in the different projects and the funding that we have received to be able to carry out this research, and to all of you for listening today. Thank you.